Now, that will work for something going through here, and here, you can pass that around. Another application for that is this guy, which is kind of similar. What happens here is we have a coil of wire, which when we energize it will create a magnetic field. And if you put a ring on that, what's going to happen when we turn on the juice? Pardon me? Okay, yeah, can you speak up, Brennan?
It's going to oppose
Yeah, there's going to be a big magnetic field here. And what this ring is going to do, there's no magnetic field now, it's going to try and oppose it. So if, let's say, the magnetic field here is going to point north, or have a sort of north type of magnet, then this ring is going to try and point down. So, and essentially it's going to be like two north ends of a magnet, two north ends of two different magnets pointing at one another. And since this is very lightweight, it should go fine. We'll see. So this is are you ready? Hey.
Oh no.
Always plug it in.
Ready?
Yeah. Whoa!
Whoa. Nice.
So that is what's popularly known as a railgun. So unfortunately, we're leaving bunts in the ceiling.
Do it again.
Yeah, once more. Healing. And ooh, I'm getting dust in my eye. Ooh, from the ceiling. Yeah. So this is an application of the Lenz's law. That the current in here is opposing the magnetic field in here that's being generated. And so if you make these really lightweight and you make this a really strong field, you can accelerate current loops up to really high accelerations and punch them through walls of tanks and things like that. So that is the idea behind the railgun. And once more.
Oh,
Did leave it then. Okay, so that is the railgun, and that's sort of the application of the Lenz's law. Now, the current in here is actually what we call alternating current, and I'll show you a little bit how that actually. So this is probably good to do is when you explain the copper tube and the ring tosser. And you can actually calculate the magnetic field EMF induced on these coils. And that's actually what the next part is. It should be pretty quick, actually. What the EMF in a rotating coil in a magnetic field. And this is how generators work. And in fact, we have a generator example over there. So you need to be able to explain how a generator works. Basically, what happens when you change the generator frequency, we'll do that directly, and what means by the root mean square. This we'll just get to that, I think, and the relation between peak and RMS. So, how you use this for a generator is, let's say you have a magnetic field here, and you have a current loop here, like a wire that's going around. The flux through this wire, and we'll say this green arrow is the direction of the area. The electromagnetic flux will be the change in phi, the change in magnetic flux, times the number of loops that you have. Right here we have loops equal 1. So the flux is this, NAD, and where N is the number of loops, cosine theta. We want the change in flux to give us the electromagnetic force. That change in flux we can divide by delta t. This is like a derivative, right? So if we're taking the derivative of this with respect to t, you guys are all experts in trig derivatives at this point. You get NAD sine theta d theta dt, or delta theta dt.
Isn't it negative sign?
There is a negative sign. Excellent, Dan. Excellent. And in fact, that actually, so there's a negative sign here, so it should have canceled out.
Gotcha.
So you get that. And then theta, we talk about omega as the angular frequency or angular velocity. The angle is just the angular frequency times the time. So instead of having d theta dt, we can have, if you take d theta dt, you get omega. So we can say this is just NAD omega sine omega t. And this gives you the EMF that gets generated by a rotating coil in a magnetic field. And it gives you a sinusoidal dependence of the electromagnetic force. Now you use that in like this application, and this is kind of like a rotating coil. Usually you use many hundreds in here. And you can imagine that you take two wires out, one from each side of the coil. As you're turning this, you'll get different voltages, or you have a different voltage potential, electromagnetic potential between those two wires. And as you rotate this thing, you'll actually get some energy. You'll get different voltages, and that's what this kind of thing is. That there's a rotating coil in here. They're magnets in here, and as you turn this, you actually can get some light, and so that's actually what this is doing. Is we're turning many coils through a magnetic field and generating some voltage, and so that voltage will come out like this. It will come out with a sinusoidal dependence, and that is what we call alternating current. So from a coil, we'll get the, and I think this is actually in your data book. This is and this gives out alternating current, what we call alternating current. And you can see that briefly in.
We ran out of room on the camera for more recording, so I'm just filling in with some slides here. The point of this slide is that the voltage that comes out of the generator alternates from positive to negative, and that's why we call it alternating current. Although alternating voltage might be a better description.